So yeah, I'll be talking about hardware-software co-simulation and complex system development with Renode, which is an open source framework that we do. And as a company, there's a lot of things to be said about us, but I think the most important thing is highlighted in red here. We want to avoid proprietary workflows and tool chains, not because of spite or some, kind of weird emotional attachment to open source, but rather pure pragmatism. We want to automate, script everything that we're doing. And of course, proprietary software is preventing us from doing that. So instead, we're trying to figure out how to do things more open source. We participate in lots of initiatives. We're a Platinum founding member of RISC-V, and I'm actually, since yesterday, vice chair of the marketing group. So you can always talk to us about doing cross-promotion and kind of building out the ecosystem and kind of connecting different projects together and so on. We're part of FOSSI too as persons, but since there's no corporate sponsors yet, then I can't say we're members of FOSSI, but personally we are. We do lots of things in different areas. It's both FPGA stuff, it's operating systems, but mainly I want to talk about methodology, because in each of the other areas, we eventually arrive at the problem that methodologies are preventing us from iterating faster. So if we fix our tooling stack, if we fix the way we work, all the other things become simpler. So why do we need hard software code design? The answer is pretty simple. We need more and more and more features and more software to be available out of the box. And some people complain, say, oh, why do these software people need all these operating systems and everything? But we actually think it's a good thing to expect a lot from your hardware. It's a good thing that people expect the hardware to ship with software from day one. And we want to enable that. And RISC-V, for example, and open hardware in general, has this promise that more openness and more configurability will help with this software-driven method that could get us there. But it's not enough. Just having open IPs and having open CPUs isn't enough to fix the entire problem. We need tools and methodologies to be in place to leverage the fact that we have open cores and open IPs. And that's what this track today is about. So we actually need more parallelism in development. We need more feedback loops. We need people to be working together. We need to catch bugs early. And we need also to kind of improve the relations between different teams in companies and even across companies so that less people can do more. That's one of the reasons why we did Renode in the first place. I mean, of course, all these grand things were not in the scope necessarily at the very beginning, but we had this hunch that, it's weird how software and hardware is being developed separately, and it's so hard to sometimes develop software because you don't have the hardware, it's not very replicable. So we thought, okay, we need something else, we need something new. We were looking for a flexible simulator that would give us the possibility to run different kinds of software without modification, support many flexible platforms, particularly softcores, which we had been working with since the very beginning of the company, which could build like entire board simulations and perhaps even multi-board systems, have this kind of plug-and-play multi-block nature. And we also wanted something scriptable and API-oriented. And there wasn't anything like that out there, so we went out and built Renode. It's actually 9 years in development, so it's not a very young project, but I'll just tell you a few words about it. It's an MIT licensed framework, and as the basic part, of course, there's an ISS, dynamic binary translation simulator. That's the core of the things we do. But then, on top of that, is a multi-layered and API-based and modular and building block-oriented framework. And this framework that we built has a strong background in real use cases. We're working with a lot of ARM systems and increasingly so in RISC-V systems, which we're very happy about. So we give it a commercial backing and we kind of use it ourselves to make sure that we're not talking nonsense and giving people a tool that doesn't do stuff they need. We support lots of platforms here and there. This is mostly based on our past projects and use cases we found and customers we found. But we don't want to be exclusive to, like, say, we're a RISC-V simulator or we're an ARM simulator. We are okay with some of the different things. There's, of course, a focus. The focus is mostly with like new RISC-V platforms recently, as well as a lot of like Cortex-M style ARM microcontrollers. But we also have things like Leon or Zinc. We have different customers, but there's 3 of them that have been particularly contributing in a major way. Microchip, Google, and Intel, all of them working in different areas. But actually, all these kind of contributions and the sponsorship of our work has kind of aligned nicely to get a lot of stuff done that actually all of them could benefit from between each other. So what Renode does is kind of, we have a modeling framework where we build peripherals, we have cores, and then on top of that, the regular user will not be expected to actually write a lot of code, right? You'll be able to take those building blocks and assemble them with a very flexible format. It's just a text file where you just specify how things are connected. And of course, we're talking about instruction set like register-based simulation. So I'm not talking here about like cycle-accurate, very hardware-near stuff. I'm talking about a fast simulator that is used for software development. Having said that, we understand that in order to do good software development for complex and configurable systems, you have to build a configurable simulator, right? It can't be like hard-coded to do the thing you need. It needs to be very hackable. So that's what Renode is. We have the possibility to do Python scripting. So if you want to avoid modeling a given peripheral, you can just write a quick Python hack and it'll work. It'll fulfill the APIs we need and just say output a value if you need this. So all of this is in scope, and we actually want to target this FPGA co-simulation use case and work closely with people actually developing IPs so that Renode answers those needs too. It's not just stuck somewhere in the software world where nobody understands really what hardware is about. So we have those multiple layers we operate on. And of course, for you, probably here, the most interesting aspect is like the system on chip aspect. You have a core or multiple cores, and then you connect some peripherals around it. And we're very flexible at that. We have even experimental UI where you can kind of do that, plug and play style. But of course, most of the stuff we do is command line driven. The UIs are only kind of a sugar coat on top. Then you can go to an entire device, right? That's a major difference from a lot of the things other people do. So we can build a board that includes a sensor or a screen or a radio module. We model entire boards. There's a few examples you might recognize. And we can even go to a complex system. So we can even connect multiple boards over wired or wireless interfaces. And again, we can kind of visualize this kind of system. This is actually connected over UART because in the RISC-V world, it's hard to find multiple platforms that can connect over anything other than UART. It's going to change. I think Ethernet is kind of coming along pretty nicely. But for example, wireless platforms are not yet there, right? So if I wanted to show you a RISC-V wireless example, it's just not possible to do in the real world. We could, of course, do it in Renode. We could pretend there is such a platform, just put it together from the building blocks we have. But we try to work with real platforms that do exist as much as we can. And then, of course, you can run this multi-node system. You'll get a lot of console windows popping up, and you can do, this is actually showing, communication between the two devices. You can also, plug into different tools like Wireshark and analyze packets that are flying through a simulated Ethernet network or a wireless network. So lots of capabilities there. You can also simulate an environment where there's a temperature that your sensor is measuring, for example, and then you can make your whole system react to that change and do things. So we really are targeting like application software also. We want to enable an entire lifecycle, not just the low-level pre-silicon development that you do first, but we want to keep using Renode and as they're developing their stuff into more and more complex scenarios, to keep the same workflow so that they can more actively collaborate and feed that data back to the hardware development. And ultimately, I was showing you all those console windows and UIs, but the interactive workflow is one thing, but we also want to enable a more like test-driven development, and not only for software people, although embedded software are the key users, I think, but also in the more general terms. And I'll show an example of how one of our customers do it later. And to enable this continuous integration stuff, we actually integrate with Robot framework that does testing. Of course, we could do some other frameworks, but Robot is our first choice. It's a Python-based framework. You write tests in a fairly simple language, and then you get nice reports out of it, all open source, of course. And then on top of it, we also are building a testing system in the cloud. So we want to offer this as a service over time, so that basing on our entire open source framework, we want to kind of have a way to offer people a pre-configured way to do their testing. But of course, you can take that and do an on-premise installation as well without a problem. And then if you run a test, you're going to get the results, but you can also get save points, like you've been developing a system, you run a test, and you want to see what happened, like a test failed, I want to see what happened. You take this file, you load this file in Renode, and the entire system just pops up as it was in the moment that the save file was made. So we have a couple of those super cool, like developer-oriented features that really help when you want to do something quickly. So now I'm going to talk about some important new developments. We've done a few things that should be especially interesting to you. I won't go through them right now. I'll just kind of start talking about them one by one to save time. So the first one, a big one that was announced at the last RISC-V summit, is supporting the microsemi or microchip PolarFire FPGA system on chip. And the reason that it's really cool is that it's RISC-V based, right? So that's a very important thing. Microchip has been a major sponsor for RISC-V, so we're pretty excited about that platform. It's multi-core, has as many as 5 cores, and a pretty good and big FPGA inside. So the first platform that Microchip had for developing this was this big board. It costs $3K, and it's not really very handy. So they knew that they couldn't scale that, right? They couldn't just give everyone a board. I assume that from all of you, we're not a good representation, of course. We're hackers, and we probably know these guys pretty well, so there might be a few people with a board like that here in the room. But in reality, if you want to scale that to thousands of developers, it's not possible. So instead, Microchip sponsored the development of their platform in Renode, and so anyone can go to GitHub now and download Renode, and the platform is there. And it's an important platform in the sense that it has a lot of infrastructure. There's a lot of peripherals, lots of APIs we had to improve and build out to make it supported. We have PCI Express, we have USB, we have Ethernet. It's really, connectivity-wise, it's very, very cool. And also, since it has an FPGA, this kind of co-simulation aspect is very much in focus. And that's really good, because having this in focus from a commercial customer helps us to do incredible things. And we went on and did integration with Verilator to actually co-simulate IPs in the FPGA. So people will be building new stuff on the PolarFire SoC, building new IPs. They'll be able to plug it back into Renode and simulate their IPs in Verilator, perhaps over time also build a model in Renode. That's also, of course, possible. So this co-simulation capability has been built pretty recently. The co-simulated block, we need to wrap around this a little bit, but it's pretty simple. And then we can actually drive it from Renode, fulfilling all the APIs, so it's going to work as if it was a real native Renode block. And you can simulate most of your design in Renode in a fast way, and then just offload a little part of it to Verilator so that it's pretty fast. And we've done that, and suddenly everyone's interested. Like, there's so much interest in this feature. It looks like this. I've shown you this, format before, so you can just connect this UART to the system bus on some address. You kind of point it to the shim layer that you've made. It's a very simple one. And voila, you have a simulated UART. And this actually works pretty fast. I don't have a video here, but this presentation links to that video. And you can just use it as normal. Microchip has also been a very interesting user. They've been doing a lot of interesting experiments, implementing their own models, and doing some kind of visualizations of, we have a lot of data, right? We can kind of take all this data and show it to the user. We can trace the CPU, we can look at memory, we can visualize calculations. It's pretty cool. So the significance of the platform, as I said, it's an FPGA SoC platform, so naturally very good for prototyping. People are it's like the Zinc of RISC-V, more or less. It targets like both Linux and real-time systems, which is good because Renode wants to do all of these things, and it targets AMP systems, very good as well. We can do that. So yeah, we think in general it's going to be really great, and we're also kind of already on the pre-silicon level. So before the chip is actually available, it's coming next year. We have people already doing development, and we want to show with this platform how you can do pre-silicon development and continue over the entire life cycle of the product, working in this hardware-software co-design loop. Now, the second thing I want to talk about, it's a demo that we've been showing at the RISC-V workshop. It's an Ethernet bridge to an FPGA. This FPGA is FOMU, which is the FPGA in your USB port. It's a really small board by Mithro and company. It's a 5K LUT FPGA essentially, and what we were showing, but we also can show it to you if you want during break. we have this, it's really here. You can't see it, but it's inside this. And also I'll show you the FOMO right now. See, very nice, but you need a looking glass to see it. We are bridging from Renode into the FPGA. Most of the system on chip is here, and just one peripheral controlling the LED. The LED is blinking, you have to trust me. Again, the video you can see when you click this link. We can control this LED either from Renode or from the software. There's a lot of choices, but in general, this peripheral and this LED, they don't know that they're being, they're operating in a system that's being co-simulated from a PC. For them, it's just the same. And again, we did that, and everyone's interested, right? Everyone's like, NXP's coming, oh, this is great. And also, to make it even nicer, we actually have FOMO as a giveaway, and I think there should be high interest in this group. So basically, come to us and tell us what you'd like to do, like with FOMO or perhaps with FOMO and Renode, and we're going to give you a 5K lot FPGA you can progress with open tools, and yeah, so some of you already have some, but I'm sure that there's more interest than that. Other developments have been new FPGA soft cores and soft system on chips. So we've supported things like PicoV, Vectors 5, and Minerva, and system on chips like Murex, Picosoc, Litex. They can mix and match a little bit. Not all of them go with all of them, but in general, we want to enable with Renode that if you build this weird combination of things in your FPGA, it's okay for you to also try to run this in Renode, and Renode allows to kind of mix and match those things. We've also, because of working with these topics, we also had to introduce a couple of things like customer instruction support, custom CSRs, handling of interrupts that varies from core to core, and we all want all these things to be as configurable as we can, so that we can support a variety of soft SoCs. So, for example, for PicoV, which is a pretty non-standard core, it's very small and nice, but also not kind of very RISC-V-ish sometimes. We had to do this non-standard interrupt handling, additional queue registers that also work with the interrupts. We had to handle the timer in a specific way because it wasn't, again, done according to the spec, which is fine. Like, we want to enable these use cases. I think the primary citizen of all the soft cores we're enabling is Vectors 5, which can run as part of the Litex SoC. And the reason is this is both like Zephyr or RTOS capable in general, but also Linux capable. And 32-bit Linux is a pretty good thing to have in an FPGA. So Vectors 5 actually won last year's RISC-V soft CPU contest. And in Renode, we're modeling not just the CPU, but we're modeling also the stuff around it in Litex. So we're modeling the Ethernet peripheral, the UART, and we could build pretty complicated setups with it. And also, because of the very little integration, we can think of even extending this with additional things and potentially then contributing back to Litex with new peripherals. So Renode has been instrumental in the 32-bit Linux works we've been doing. So before the summit last year, for the hackathon that Western Digital wanted to organize, we collaborated to try to build the 32-bit Linux. It was very hacky. It was a very fast and hacky experience, but Renode helped us to implement very basic Linux. And then this work was taken over by Dave Shah, Florent Kermarek, and Charles Pepin, and they kind of got it to work with mainline Linux in the end. So through this collaboration, we actually got to something really nice. We have now Linux on Vectors 5 running in an open source FPGA. So this kind of is also being plugged into the main foundation, RISC-V foundation work. We're trying to kind of make it visible to everyone, and this is the RISC-V Getting Started guide, which we, as you can see, put the Litex Vectors 5 stuff into. And you can both run it on hardware, but also in Renode, and we're trying to do it as parallel as possible. So you take the same binaries, you run them in Renode instead of hardware, and it should work the same. I don't know how I'm with time, because we've been delayed, so not sure how much I can go on. -5? Okay, so I'll try to be quick. It's the last thing, so don't worry. So Dover Microsystems is a use case that we've been working with a lot, and they're really cool because they're developing an IP that's actually under tape-out by NXP, right? So it's a pretty serious thing. And this security IP they built, they needed to control execution of code really closely, and they needed to do lots of things. So they have this system that tries to protect the CPU with a policy enforcer. This is a very complex, hardware software co-design task. And they do, with Renault, they do both design space exploration and implementation and testing, but they also deliver it to customers, and their customers then also work with Renault. So they have this flow where they do both like Renault development before they actually do the hardware development, and they use this feedback loop to improve the hardware development. And they actually went from several, days or weeks to develop a feature to hours because of that. So they've really been able to improve, and they also test hundreds and thousands of tests every day in Renode to make sure that their IP is working. And they've been working with things like cache profiling, testing boot code, building fairly complex systems with video, where they used Renode to do all the software development before the hardware was even there. So they're doing really incredible stuff, and I think it's a good proof that their hardware and software teams suddenly collaborate much, much closer than they used to, and they're very happy. Yeah, so go to GitHub, get Renode. It's 1.71 now, probably soon .2. We have documentation. There's always too little, so you can help us and write a bit. And yeah, we generally just want to enable these weird use cases that you might have. So don't worry and reach out to us and tell us what you're trying to do, and we might be able to tell you that, yeah, Renode can do this already, or it's not that hard to do this. And we think that actually the modular and open source hardware is really helping things like Renode, because we're also very modular and open framework, so these things really go very well together. Yeah, I think I'll finish with that, so I'll give you some time for a break.
Do we have a quick question?
Everyone's hungry and thirsty.
So this sounds quite interesting. If a third party wants to add support for a different board, how easy is that?
It depends on if the building blocks are there or not, right? If the building blocks are there, it should be trivial, because you just write scripts to assemble them. If you need to actually add peripherals like models, then there is a learning curve, but we try to make it as easy as possible. So when you're modeling a peripheral, you're essentially kind of implementing a data sheet from the other side, so to say. So you're trying to implement a functional spec, an API towards the software. We try to make it as simple as possible, so you can inherit from classes that already exist. We have, kind of, say you want to build a SPI peripheral, right? It's going to fulfill some interfaces for SPI and so on. And you have to, of course, write the stubs of the functions that we provide for different kinds of communication. But it should be fairly simple. Like for us, normally writing a peripheral is, a couple days. Depending on the complexity, right? If it's a radio with thousands of registers, it's going to be, of course, a much longer experience, but that's just purely related to the complexity of what you're trying to model.
There are no other questions. It's time for a coffee break. We will reconvene at 10:50 and continue with the session. Thanks a lot. Enjoy your coffee break.